Welcome back, students, to another lecture of Mineral Beneficiation MTT 205. And for today's discussion, we have the topic Liberation and its significance. Moving on, you can see the syllabus for this particular module. We have liberation, communication, size and its classification. So, all about this module is all about size reduction of the particle into finer bits. So we have the initial topics like liberation and significance, and particularly we will be discussing that topic today. And we have certain crushing unit as well as some. We have to study about some equipments regarding liberation operations, and we have kick and Tinker's law. Those are certain laws related to crushing and grinding operations. And moving on, we have the same topic its recent development in crushing and grinding. We have to understand what is the washing and sorting method normally used during this liberation and comminution process. And we have certain theory and practices of ball mill, types of mills, and there are different types of mills we have to study for this particular module. And we have a laboratory screening equipments. We have to go through that also. And so this module is all about classification, liberation, and combination. For the introduction, the term liberation. So what is the literal meaning of liberation? It can be defined as a freeing or detachment of something. You already have heard the word liberation in the history classes, like liberation, women liberation, poverty liberation. So it is like the word literally means freedom. Okay, so in our context it can be defined as freeing or detachment of dissimilar mineral grains. So you can see that this is kind of this is the example ABC. We have to go through what are the terms A and B and C. The operation employed to liberate the dissimilar materials in the size reduction or combination. So this process is like disintegrating or detachment of dissimilar mineral from the particular ore. So that is the process of liberation. So for here we have mineral A as the valuable minerals, and mineral B and C are the gang materials, that is the unwanted materials. So our aim is to get disintegrate the material A from this particular ore. So that is our initial and the first process. So how we are able to do that? So this is the process. Various mineral grains, you can see different types of grains present in this particular ore. They are physically combined. So as you can see, this is physically combined. And in order to detach the valuable mineral, what is the main objective for us? Reduce the size of the ore particles. So in order to extract a material or a valuable mineral from this particular ore, we have to reduce the size of the ore particle. So that is our first objective. So in liberation, we have an operation called liberation by detachment. So what that particular term means? It's a physical property of the adjacent mineral or significantly dissimilar. So you can see from this ore that we can distinctly differentiate what is A, B and C. So the bond between them is not notably weak. So that means the bond between the particle is weak. We use this particular factor in order to disintegrate the particle. We go for fracturing the particular ore, that is nothing but disintegrating the particle with the help of force, and detachment of the mineral after the processing, and hence ultimately we are getting minerals out from the gang material. So this kind of process is called liberation by detachment. So nothing but taking an ore, and in order to detach the mineral from that, we apply external force, that is like fracturing, and due to this fracturing the whole ore will get reduced in size, and we ultimately reduce the size of the ore particle, and from there the valuable mineral will be detached, and this kind of process is called liberation by detachment. So in order to explain this process, liberation by detachment, we have an ore here. So this is an undefined shape. So if we go for a defined shape, we can explain liberation by detachment much more easy way. So we have a ore like this, whereas the dark portion denotes the valuable mineral particles, whereas the gang material is shown in the white portion. We can detach this particular ore by the process of fracture. As we mentioned earlier, we can incorporate fracture into this particular ore. So imagine a fracture is happening as I shown in the arrows, yellow arrows shown here. So you can see that, imagine the particle is getting fractured this direction. So initial dimension of this particular ABCD is 8 into 8 centimeter. So one side is 8 centimeter and the other is 8 centimeter square. Just note that in this case, the grain size, the particle size and liberation size are equal. So we are going to explain A, B and C. So make sure that in all cases the grain size and particle size and all are in the same dimensions. And in order for explaining the process more easily, we are using this particular case. The grain size we are taking in a uniform pattern. So after disintegration process, what we are obtaining is that this 8 into 8 centimeter square is disintegrated into 2 into 2 centimeter. You can see that, you can clearly distinct this square box. This is 2 centimeter. So along with that, we are adding 2 into plus 2 plus 2 plus 2 gives 4. So after fracture, this particular 8 into 8 centimeter square will be turning into 2 into 2 centimeter. That is, each side will be 2 centimeter each. So what is the advantage is that we can clearly distinguish what is the gangue and what is the valuable minerals from after this process. So in the previous case, we had the disintegration process and the fracture process happening in this particular direction, and in here in the case B, we have the disintegration or fracture happening as shown in the yellow lines. This pattern is different from the previous pattern. So what is the ultimate liberation method liberation process happening is that we are yielding a 25 particles, out of which 4 particles, you can see E, F, G, H. This process, after liberation process, we are getting 1 into 1 centimeter size particles. You can see that, imagine this is 8 centimeter, then one small particle like this, as my mouse pointer is moving, you can clearly see that that is 1 centimeter particle. And we will be getting, after this fracture process, we are getting 25 particles. Among them, this particular EFGH will be 1 centimeter, and we will be getting 12 particles of size 2 into 1 centimeter. So this is 2 into 1 centimeter particles. The rest of the border particles can be considered to be as the 2 into 1 centimeter dimension particles. So these are 2 into 1 centimeter particles, and that will be 12 particles, 1, 2, 3, and we have 4 side. So 4 into 3, that is 12, and the remaining 9 particles will be present in inside portions, 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally we will be getting 25 particles yielding out. So you can see that here the liberation process is much more. We are yielding much more particles, and the process will be helping us to separate out the valuable as well as gangue material further. So in the third case, we go for a fracture process like this, longitudinal as well as transfer direction. Then the ultimately yield what we are obtaining is 64 particles, or are all are free particles of 1 into 1 centimeter size. So each square particles will be 1 into 1 size, and out of which 32 are valuable minerals and 32 are gangue materials. Liberation is all about reducing the size particle size of the constituent ore. So you have seen 3 different types of liberation methods we have used. So we will be incorporating this method in the further discussion. So next classification is transgranular liberation. So as mentioned earlier, this particular ore, each particle like A, B, C are distinctly, we can distinctly classify, distinguish between what is A, B and C. The physical properties are not much similar. So we can clearly distinguish what is A, B and C. But imagine a case where the physical properties of the adjacent minerals are not so dissimilar. That means they are similar. In that case, rupturing process or the bond breaking process will be difficult, and the fracture occur across the grain, producing locked particles. That means the physical properties are not much different from each other. So the process of liberation will be difficult. Hence, detached valuable minerals, the ore is further reduced in size. So what is happening is that since the process is not that much efficient when compared with the other case, I ended up in reduced ore consist of free particles of valuable minerals, that is the needed the valuable mineral we need, but hence But unfortunately, along with that, we have few locked particles of valuable minerals as well as gangue materials, and free and locked particles of gangue materials. So along with the what we want, ultimately what we want to extract out from the ore, along with that we have some other elements also, other minerals also. So this is termed to be as transgranular liberation, and most of the liberation operations of the ores comes under this category. So this is a common operation. So since this process is happening like this, we have to study how this process can be efficiently done in order to extract the valuable minerals. So we have to go in deep about those processes. So next important topic is the size reduction process. So size reduction, why we do size reduction? So size reduction of ores is not normally done in order to liberate the valuable minerals from the host rock. That is the initial or what we are getting. So from the image, the figure, you can see that this is the y axis will be showing the size, and that is in mm. And initially we have size larger than 1000 mm. The particle size will be very huge, the rocks will be very big in size. We have to reduce that particular big lumps of ores or lumps of rocks into finer bits. So that is our objective. So the initial equipments or instruments we are used for reducing the size are jaw crushers, primary gyratory crushers, and we have further crushers like cone crushers. There are HSI primary and secondary crusher unit. Different type of cone crushers are there, and ultimately what we are obtaining from this particular graph is that initially we will be incorporating this kind of equipments in order to reduce particle size greater than 500 or 1000. And moving on, we will be having small scale units of crushers, and ultimately we are obtaining very fine particles. So you can see that the size reducing is shown in terms of this graph. The size will be it will be high in the curve, and it will be going down. And the liberation size will be, the maximum liberation size is that 100 to 10 micron. That is the ultimate size we can obtain after liberation process. After that we have to go for grinding. So this is then so imagine a process required a particle size in the range of 8 to 4 mm. So in order to reduce the further size, we have to rely on grinding process or grinding mill. So we will be using grinding mill here in order to reduce further size reduction process. So it's a combination of size reduction is a combination of crushing as well as grinding operation. So moving on, we have some of the equipment used in general application of crushing as well as grinding operation, and the actual range depends upon the material property and the process requirement. And you can see here also the particle size in millimeter, and moving on we have micron scale, and moving on we have size reduction 100 micron. From this 100 millimeter, it is getting reduced to finer size. And we have different type of crushing as well as grinding unit. Crushing unit, we have jaw crushers, gyratory crushers, cone crushers. Moving on, we have semi automated grinding mills, and we have rod, ball and pebble mills along with that. And here you can see this is an attrition mill. Actually this kind of equipments we'll be discussing in the further lectures. But so as mentioned here, we have different kind of instruments used. But what are the ores we are adding? What are the what all, how we can decide which instruments is required? So in order to do that, we have to understand the nature of the ore we are using. Or we have three examples here shown here. Imagine for the example massive ores. Imagine a massive ore. In this ore, the reasonable amount of the crushing makes the valuable liberator. For example, take an example of coal or an iron ore. There will be this ore will be reasonable amount of crushing required in order to separate out the valuable minerals. Whereas we have a next classification called interground ores. In this particular ore, we have a process like crushing, along with that the certain amount of grinding also required in order for the liberation. And for example, we have chrome ore. So depending about the ore we are using, the process will be varying accordingly. And the final classification like disseminated ores. In this particular ore, they are sparely distributed through a waste, valuable as a sparely distributed through a waste rock matrix, and requires fine grinding to liberate the valuable ore. So best example is gold ore. You can see that it is not economically, like it will be, it is not an easy process of extraction when you go for gold ore. So in order to do that, we have to disseminate each ore into finer bits, and in order to do that, we have, so how are we going to do that? We use fine grinding, and ultimately we liberate the valuables from this particular ore. So this is the three classification of ore we feed into the liberation operations: massive ore, underground ores, and the disseminated ores. So it is a natural tendency of a mineral have a tendency to break into endless number of sizes and shapes every time they introduce to energy. Imagine a ore is like this, and we are incorporating a kind of energy in terms of fracture or force. We are applying a force. So it is a natural behavior of a mineral to disintegrate into finer bits. So this is a natural process. And what is the difficulty for a mineral dressing engineer is that, imagine we have a certain designation, we have a certain requirement, like this ore should contain the particle size to be like this. So that is our part comes, how to reduce the large lump of ore in order to reduce into a correct required size. So that is our difficulty, and that is shown here. Difficulty in size reduction lays in the art of limiting the number of over and undersized parts sizes. So we should have a uniform particle size. So that is our limiting that is our difficulty for size reduction operation. If not controlled, the mineral will follow its natural crystal behavior. That is, we can't. You can see from this particular graph, the particles will be either forming into a larger lump or a finer bits. So we can't control the each particular stages when we go for the natural process, but we have the equipments and we have the science how to reduce the particle size in a certain uniform matter process. So that's why we are using different type of grinding as well as crushing units. So with that, we come to the end of today's lecture. So these are the reference used in order to make this particular PPT. Thank you for listening. I hope you find this useful. Hope to see you guys soon. Thank you.